In 2022, a woman in her early 50s walked into a routine screening at Moorfields Eye Hospital in London. She had no symptoms, no pain, no alarming blood work. Every physician who reviewed her case gave her a clean bill of health. But an artificial intelligence system called DeepMind's ORCA had already flagged something in her retinal scan, a pattern invisible to any human eye, that pointed to early-stage pancreatic cancer. She was diagnosed and treated successfully. The doctors who later reviewed her original scans still could not see what the AI had seen. That gap between what machines perceive and what humans can is now reshaping the entire architecture of modern medicine. Here is why that gap matters right now. Today, not in some distant future. Pancreatic cancer kills roughly 50,000 Americans every year, and 90% of those deaths occur because the disease is caught too late. When it is found at stage 1, the 5-year survival rate is close to 40%. When it is found at stage 4, that number collapses to 3%. The difference between those two outcomes is often nothing more than timing. Weeks, sometimes months. We also have a collapsing medical workforce. The United States is projected to face a shortage of up to 86,000 physicians by 2036. Radiology departments in rural hospitals are already reading scans with skeleton crews. The question is no longer whether AI belongs in the diagnostic process. The question is how quickly hospitals can deploy it before more people die waiting for an appointment that might have saved them. To understand how an AI catches what doctors miss, you need to understand what doctors are actually doing when they read a scan. A radiologist reviewing an MRI is looking for deviations from a mental template built over years of training and practice. They are pattern matching against thousands of cases stored in memory. The problem is that human memory is lossy. Fatigue is real. Context bleeds in. A radiologist who has reviewed 60 scans in an 8-hour shift is measurably less accurate on scan 60 than on scan 1. Studies published in academic radiology show error rates climbing by as much as 30% late in a shift. AI systems do not get tired. They do not have bad days. They were built on a fundamentally different architecture, not training on a few thousand cases during residency, but on millions of labeled images processed without blinking. Think of it this way. A seasoned radiologist might have deep personal experience with 10,000 scans over a career. A model like Google's ORCA was trained on over 1 million. That is 100 times the exposure, with perfect recall on every single one. The first revelation that stops most people cold is this: the AI is not just faster. It is detecting signals that exist below the threshold of human perception entirely. In a landmark 2023 study published in Nature Medicine, researchers tested an AI model against 44,000 mammograms from women in the United Kingdom and Sweden. The AI reduced false negatives, missed cancers, by 26%. It also reduced false positives by roughly 13%. But here is what made researchers genuinely uneasy. When they asked radiologists to review the cases the AI had flagged as cancerous, but they had originally cleared, many of those physicians still could not identify the anomaly even after being told exactly where to look. The AI was responding to subpixel density variations, microcalcification clustering patterns, and tissue texture gradients that do not correspond to any named feature in a radiology textbook. It had learned to read a language that humans never wrote down because we never knew it existed. And that raises an uncomfortable question about the 4 years of misdiagnosis referenced in that woman's case. Because it was not one radiologist who missed it. It was a system. The deeper revelation is what happens when you extend this logic beyond mammograms and retinal scans. Research teams at MIT and Harvard's Mass General Brigham have demonstrated AI systems capable of predicting breast cancer up to 5 years before clinical detection. Not from tumor imaging, but from the structural patterns in healthy surrounding tissue. The tissue itself telegraphs future disease in a way human eyes simply cannot decode. A separate study from the University of Pittsburgh, published in 2024, showed an AI predicting Alzheimer's disease 7 years before symptom onset using nothing but a standard MRI, achieving an accuracy rate of 82%. This is not marginal improvement over human performance. This is a fundamentally different category of diagnostic capability. To put that in terms you can feel, imagine being told in 2019 that you would develop Alzheimer's by 2026, with enough lead time to begin treatment during the window where intervention still changes outcomes. That was impossible 5 years ago. It is now a clinical reality being piloted in 3 hospital systems in the United States. The mechanism behind this capability is something called a convolutional neural network, or CNN, and understanding how it works will change how you think about what intelligence actually is. A CNN processes an image not as a whole picture, but as a hierarchy of nested patterns. At the lowest layer, it detects edges. At the next layer, it assembles edges into shapes, then shapes into regions, then regions into structures. Each layer builds abstraction on top of the one below it, and the network learns which combinations of lower-level features predict meaningful outcomes at the higher levels. What makes this counterintuitive is that nobody programs the features. Nobody tells the network what a suspicious calcification looks like. The network discovers the features itself through exposure to millions of labeled examples, through a process called backpropagation. Essentially, the system gets a score on every prediction, measures its error, and adjusts millions of internal parameters fractionally until its predictions improve. It is closer to how a child learns to recognize faces, through repetition and feedback, than to how a programmer writes rules. The result is a system that develops its own visual vocabulary, one that may have no equivalent in any medical textbook ever written. The complications are real, and they deserve serious attention. The first is the black box problem. When an AI flags a suspicious mass, it cannot always show its work in a way a physician can audit. The EU's AI Act, which came into force in 2024, classifies medical AI as high risk and requires explainability. But current explainability tools like SHAP values and gradient heat maps are still crude approximations of what the model actually computed. If a system is wrong, and it will sometimes be wrong, the physician in the room carries the legal liability for a decision they may not have been equipped to second-guess. The second complication is training data bias. Most large medical imaging datasets are drawn from academic hospital systems in North America and Western Europe, which skew white, urban, and insured. A 2021 study in The Lancet found that dermatology AI systems trained on these datasets performed significantly worse on darker skin tones. Deploying a system trained on a biased sample into a diverse general population does not reduce inequality in medicine. It can entrench it. This affects you more directly than it might seem. If you work in radiology, pathology, or any diagnostic specialty, the trajectory is already visible. The FDA had approved over 700 AI-enabled medical devices by mid-2025, the majority of them diagnostic imaging tools. That number will exceed 1,500 by 2028 according to projections from the Medical Imaging and Technology Alliance. Your hospital is not deciding whether to adopt these tools. It is deciding which ones and when. If you are a patient, the more immediate reality is this. The hospital where you get your next scan may already be running an AI in parallel with your radiologist, flagging cases for secondary review. You have the right to ask. You also have the right to ask whether the system was validated on patients who look like you. These are not abstract policy questions. They are questions with answers, and asking them changes what happens to you. Zoom out far enough, and the picture becomes genuinely staggering. We are in the early years of a transition that will likely define the next century of medicine the way germ theory defined the last one. In 10 years, the diagnostic chain for most cancers will almost certainly begin not with a doctor's appointment, but with a continuous passive monitoring layer, wearable sensors, annual blood panels run through protein biomarker models, retinal and imaging scans read by systems far more capable than anything deployed today. The physician's role will not disappear, but it will shift from pattern recognition toward judgment, communication, and the irreplaceable human work of